Hello everybody. I would like to add a short video to the appendix A, the complex number, about a very useful operation called a conjugate. So the conjugate is basically you have a complex number and you flip that across this real axis. Right? It's a mirror across the real axis. If it's in the first quadrant, and then its mirror going to be in fourth quadrant. If it's in third quadrant, its mirror going to be in the second quadrant, so on and so forth. So here, if we look at the conjugate, if it is already in rectangular form, its conjugate denoted by C asterisk, and some the reference use a over line to indicate the conjugate. And if so, the mirror of the across the real axis is you keep the real part the same, and you change the sign of imaginary part, right? So that's the conjugate of the complex number in rectangular form. It's in the polar form. So you keep the magnitude the same or the absolute value the same, and you change the phase angle to the opposite signs. So that's the equation 6 and 7. Here is a quick demo of using the Python, and I have the number C is equal 5 plus 6j, and its conjugate. The conjugate is in the Python is just the C. There's a method function associated with the complex number, the C dot conjugate. Don't forget about this parentheses. You have to have that, otherwise it will give you weird result. But in this case, you get the conjugate of the C. So they printed this in the rectangular form. So the conjugate of rectangular form is 5 minus 6j. Right? For the polar form, I give another example called C1. The polar form is 10 times e to the power of 1j pi over 4. And it's conjugate and use same function, same method. And the conjugate in polar form I printed here, you see the phase angle is just the opposite, right? There are a couple of useful applications with this. One is when you add a conjugate to its original one, and you get a 2 times the real part. Right? If you subtract the complex conjugate from its original number, and you get a 2j times the imaginary part. So based on this, actually, equation number 8, that's very commonly used when you want to find the real part. You just add the complex number and its conjugate, and then divide it by 2. And if you want to find the imaginary part, you just subtract the conjugate from the original one and then divide by 2j, right? So this is the very useful one. And the other one is the product of the multiplication of the complex number and its conjugate. In the rectangular form, C times C conjugate is going to be equal to a plus b, a squared plus b squared. They're always going to be the real positive numbers. And in the polar form, C times C conjugate is going to be the absolute value times square. And here you can also see, compare 9 and 10, you see this r squared going to be equal a squared plus b squared, right? The equation number 9 is commonly used when you have the complex number divisions. So let's see the example, 15 divided by 1 plus 2j. And what we can do is we multiply the numerator and denominator by the conjugate of the denominator. And in this case, the denominator will become 1 squared plus 2 squared, which is 5. So 15 divided by 5, that's 3. 3 times the conjugate of the denominator 1 minus 2j, that's 3 minus 6j. This is what you would do if you calculate this complex division by hand. Of course, if you have Python, you don't really need to do anything. So here we just show this very quickly. 15 divided by 1 plus 2j, you print c, and that's 3 minus 6j. Right? So this is a short video to introduce the conjugate. I know a lot of you already learned this. If you couldn't remember this, the good way to refresh your memories. Okay, I may add additional parts to this. By this moment, I think these are the several parts already for the appendix A. See you next time.